Good morning everybody. So we were discussing in the last class about how the cement paste structure evolves and how we calculate the volume of the pores that actually form in the system. There are different types of porosities present in the cement paste. We discussed that the pores that are present within the structure of the CSH are called gel pores, and these are extremely fine, and if you start removing water from these pores it results in massive shrinkage. Whereas the water which is outside the gel is in the capillaries, and capillaries you have distinction between fine capillaries and coarse capillaries. So while you can remove a lot of mass of water from the coarse capillaries, it does not result in much shrinkage, whereas removal of water from fine capillaries causes a lot of shrinkage. Correct. We were looking at this example as to what happens when you hydrate cement. How does the pore structure actually evolve? We saw an example where we had a high water cement ratio 0.5, and we were trying to work out based on certain assumptions the extent of gel porosity and capillary porosity in the system. Okay, and we found that to hydrate completely, although theoretically 0.23 is the bound water content which is required, you actually need overall 0.42 water binder ratio or water cement ratio to ensure that all the pores in the gel, that is the gel pores, are completely saturated with water and all the cement is hydrated. So any water cement ratio below 0.42 may result in a system where you do not get full hydration, you will have unhydrated cement present. So we will take a look at one such system. Here we say that water cement ratio is 0.3. So once again we start with 100 grams of cement. So water is obviously 30 grams or 30 milliliters. Okay. Now we do not know that a certain amount of cement is going to hydrate. We have to assume that a certain amount of cement hydrates. Let us say there is some p grams of cement that is actually hydrating. Okay. So again we reapply the principle of understanding how to calculate the solid hydrated cement paste volume. So volume of the solid hydrated cement paste is equal to the volume of the cement, that is P divided by 3.15, plus volume of the bound water, that is 0.23 times P. Okay. So if 50 grams of cement is hydrating, then the bound water is 0.23 times 50, right, minus the volume reduction that happens upon hydration, that is equal to 25.4% of the bound water content, 0.254 times 0.23 P. So this works out to 0.489 P. The other assumption that we made, which is based obviously on good experimental observation, is that the characteristic porosity of the CSH is 28%. So this 0.28 should be equal to the volume of gel pores divided by the volume of solid HCP, that is 0.489 P, plus volume of gel pores. So that is your first equation. It has got two unknowns, so you need to have another equation. Okay. What is the other equation going to say? It is going to say that this 30 milliliters total water is distributed between the bound water and the gel pores. What did I tell you earlier? If cement has to hydrate, the gel porosity has to completely be filled with water. Okay. So this 30 milliliters has to go between the hydrated cement paste, that is in terms of the bound water, that is 0.23 P, plus it has got to fill up all the volume of the gel pores that is actually available in the system. So with these two equations, if you solve it, you have two equations and two unknowns. So you can solve it to get the value of P as 71.5 grams and volume of gel pores at 13.5 milliliters. In other words, the amount of cement that hydrates in the system is about 72%. The remaining 28% is simply sitting as unhydrated cement. Alright, now how do we calculate the capillary porosity? For that, first we need to find out the volume of the solid HCP, volume of the HCP totally, that means the volume of solid HCP 0.489 times P plus the volume of gel pores, that is 13.5, that gives us 48.5 milliliters. Okay. Volume of unhydrated cement is also there. Please remember that this unhydrated cement simply sits in the microstructure as a filler. Okay. So it is still occupying volume and reducing the pores. So the volume of unhydrated cement is 100 minus 71.5, because 71.5 is the amount that is hydrated, divided by 3.15, that gives you 9.1 milliliter. So capillary porosity is equal to volume of the reactants, that is 100 by 3.15 plus 30, right, 100 by 3.15 is cement volume, 30 is the water volume, minus volume of the product, that is 48.5 of hydrated cement paste plus 9.1 of unhydrated cement. Okay, so that gives you 4.2 milliliters. Now please compare this to the previous example where we had 13.9 milliliters. Okay. When you have water cement ratio of 0.5, theoretically you can end up with about 13.9 milliliters of void space, whereas when you are reducing the water cement ratio to 0.3, you have almost a 1/3 reduction in the porosity, in the capillary porosity. Okay. What about total porosity? If you look at capillary and gel pore, so here it is 19 plus 13.9, so that is 32.9 total porosity. Okay. Here it is 13.5 plus 4.2, that is 17.7. So total porosity is now reduced by almost half, to almost half of what it was earlier. What do you think is typical strength of a concrete with water cement ratio of 0.5? About 30 megapascal. What about 0.3? From 0.3 water cement ratio concrete, assuming that you are taking care of all the proper workability and everything. 50 is low. With 0.3 you may get 65 to 70. Okay. So with 0.5 you will get around 30 megapascal strength. With 0.3 you may go 65 to 70 megapascal. Correspondingly, what was the porosity we saw earlier? That was 13.5 milliliter, and here it is 4.2. So strength of concrete is directly linked to the porosity. And of course, please remember, we are only linking it here to the porosity in the paste. Apart from that, there is going to be porosity in the concrete which is external to the paste. What is the porosity that we are talking about? The voids, because of the inefficient mixing and packing, you will have voids in the concrete, right? What else? No, entrapped air is part of the voids, correct. Volume shrinkage of the concrete, but then that is being caused by the shrinkage of the paste. Okay. Let us assume we do not have any shrinkage, we have proper curing. What other porosity is present? Very important. Aggregate porosity does not play a role unless the aggregates are lightweight, in which case the aggregate will crack, right? When the aggregates are lightweight, that means the aggregate will fail before the paste fails. What other porosity? We have discussed this before. What happens close to the aggregate? There is ITZ, Interfacial Transition Zone. So there is higher porosity in the ITZ, there is porosity in the paste. All these are going to be dictating the strength of the concrete. So here we are trying to relate the capillary porosity of the cement paste to strength of the concrete. So you may not get a perfect relationship. If you look in your textbook, it would have explored a relationship between strength and water cement ratio. And one common aspect that you will find explored in textbooks is the relationship between strength and gel to space ratio. What do you mean by gel to space ratio? Gel to space ratio. Yeah, gel is basically referring to the total solid system divided by the total volume of the system, gel to space ratio. So what do you think will be the shape of this relationship? It should be an increasing relationship or decreasing? Obviously increasing, right? So it generally increases in a polynomial fashion. The strength increases as a function of the gel to space ratio in a polynomial fashion. Okay, gel does not mean CSH alone. Gel means all hydrated products plus any fillers that exist in the system. Okay? And this relationship also was first shown by Powers. He was the person who worked on exploring this relationship, and what people have found today in modern research is, after all the advanced analyses of the concrete microstructure and understanding how structure properties are related, they have come to the same conclusion that you have Powers relationship is still valid in most modern systems. Okay? So what will happen to this 4.2 milliliters of the porosity? I said earlier that in the early ages you may have water from the external curing which can actually come inside. So in this case, what is going to happen? This water that comes into the 4.2 milliliters of porosity may get a chance to interact with unhydrated cement. So that may lead to a greater hydration taking place in the system. Okay? Now we will discuss later that one of the common problems with high strength concrete or low water cement ratio concrete is its tendency to dry from within. Okay? That is called autogenous shrinkage. Anybody heard of this term, autogenous shrinkage? What does it mean? Autogenous means what? Happening on its own. And why does it happen on its own? Because of hydration of the unhydrated cement. And why is it leading to shrinkage? Of course, one is the chemical shrinkage. We already saw 25.4% of the bound water, that's chemical shrinkage. But why is this autogenous shrinkage happening? Because once part of the cement is hydrated, your pore network has become very small. The pores are small, and to hydrate any of the unhydrated cement that's still left, the water has to travel through the extremely small pore network, and that's going to lead to a lot of shrinking. Okay, so this autogenous shrinkage is a problem in high strength concretes, in low water cement ratio systems. Drying shrinkage is a problem in high water cement ratio systems, because in low water cement ratio systems there is no water to dry out of the concrete, right. We were talking about this earlier, that when the pores are extremely small, you can't drive the water out unless you reach very extreme levels of drying, or you heat the concrete so much that water actually has to come out, like 100 degrees Celsius. In normal circumstances, that water simply does not come out. So at low water cement ratios, you don't have a problem of drying shrinkage, but you do have a problem of autogenous shrinkage. So even if you do completely sealed curing, that means you prevent any drying to the external environment, there will be drying from within in low water cement ratio systems. We will talk about this later again. Okay, so some data is given for typical paste composition made with a certain water cement ratio at a certain age. So in this case, of course, we are talking about the phases right after mixing and in a mature paste. Okay, so if you look at C3S, okay, at mixing time as a volume fraction of the paste. Okay, please remember C3S as a volume fraction of the paste. You know that water will be the greater volume, cement will be the lesser volume. So within that, you have volume fraction of paste is 23.4% of C3S. In a mature paste, most of that C3S is actually reacted. So we are talking about mature paste of the order of 6 months to 1 year. Okay, technically you allowed hydration to complete over a long period of time and ensured that curing happens throughout this duration. Okay, C2S, much smaller content. Some of it may still remain unreacted. That's physically it's difficult for water to reach each and every particle of cement, right. We talked about the fact that you have the formation of the hydrated layer. This water has to diffuse through the hydrated layer and then react with unhydrated cement. So that may or may not happen. Although we saw that 0.42 was technically required for 100% hydration, here you see that at 0.45 also we don't get full hydration because you still have these unhydrated phases still remaining. Look at C3A, it went down from 4.42 to 0. We know this very well, that C3A is a highly reactive phase and it is present in microcrystalline sizes, because of which it reacts with the sulfates to form your sulphoaluminate products. C4AF, hardly anything is reacted. I told you earlier that C4AF, the reactivity is very limited because the iron in C4AF is not easily soluble. So practically it remains in the system. Okay. What happens to gypsum? Obviously it gets consumed completely by the C3A. Okay, there is no gypsum left in the system because C3A is consuming it. The other compounds, CSH, solid with gel pores, Portlandite, Ettringite, monosulphate, obviously they were not there during mixing. The formation in a mature paste indicates that your CSH is forming nearly 80% of your cement paste. CSH is nearly 80% of your cement paste. Okay. Your Portlandite is about 14%, your calcium sulphoaluminates are about 20%. Okay. So that is how your distinction is. Now here the water is given in terms of the total water in the beginning, 58.49 milliliters, percentage by volume is the volume of water present in the system. Later it gets distributed between capillary and gel porosity as in approximately the same ratio that Powers was talking about, but here it is a little bit different. Powers had mentioned that 1/3 of the water is in gel pores and 2/3 in capillary pores. Here it is the other way around, okay, because what has happened is your gel porosity is higher because of higher degree of hydration in the system. Okay. So this is how your cement paste or mature cement paste after about 1 year of hydration looks like. Okay, essentially what we are saying is your cement paste will have a greater volume of CSH and calcium hydroxide. Sorry, one thing I was wrong in is you can't total up these two, right. So CSH, this is the total CSH that is present in the system, 50%. Okay, it's not 50 plus 30, 80, it's 50% because the solid part of CSH is included in the structure of the CSH. So remainder is 20.96. So basically this 29.03 plus 20.96 gives you 49.99. Okay, so gel porosity 20.96 is included in this total volume of CSH, that is 49.99. Okay, because otherwise you are going above 100%, which is not possible. So you have to take this 49.99 separately. This 29.03 is the volume of the solid CSH without the pores. Okay, this is just an example. For this, of course, what they had to do is use certain formula for the CSH. Okay, for example, this type A CSH, the solid CSH, they've assumed a formula of 1.7 CS4H, whereas for the one with gel pores, they've assumed a formula of 1.7 CS1.6H. Okay, so that you are able to work out the stoichiometry correctly, balance the reactions, and then propose the extent of the system, extent of the element in the system. Okay, let's now look at some structures of the hydration products. I've already talked to you about the appearance of CSH. There's a little bit more examples which are given. Primarily you can visit this site, it's a very interesting site, cementlab.com, cement art. Okay, it says cement art because it's produced very interesting images in this. Of course, this is not from that site, but you can see several other images that I have included are from that site. This is a classic picture of cement paste, okay, at fairly early ages, 7 days old. This is scanning electron micrograph of 7 days old hardened cement paste at a magnification of 3500x. On the bottom left here, you see a cement particle that is surrounded by the fibrous network of CSH, as well as you see these needles, Ettringite needles. Okay, very clear evidence. Okay, on the upper left, you have these platelets of monosulphate. So you have needles of Ettringite and platelets of monosulphate. A platelet is essentially a three-dimensional object, more like a plate. Thickness is very small as opposed to the dimension of the plate. Okay. On the right, you see a very large crystal of calcium hydroxide. Okay. So again, this seems to show that your crystalline products like Ettringite, calcium hydroxide, monosulphate, these have low surface area because of their crystalline well-formed shapes, whereas the CSH does not really have a clear-cut shape. It's got a very large surface area. Okay. Again, some more evidence of CSH and the fibrous network of CSH particles that is actually existent. You see that the CSH is looking very fibrous. It does not have a very distinct crystalline morphology, and this is at very high magnifications. For example, this scale is 1 micron. So you can imagine we are looking at clusters of CSH particles which are only about a few microns in size. Okay. So again, what you have to do is understand the structure at different levels and try to relate this to the overall properties of the concrete, which is obviously a macro level. Okay. Now this is a picture from the cementlab.com website, which is CSH, which is forming on C3S particles. Okay. This is actually the surface of the C3S particles, and you can see the fibrous nature of the CSH that is formed on the surface. Now all this seems to indicate that CSH has a sheet-like structure, and there are many scientists who have worked on deciphering the structure of CSH, associating it with naturally available minerals, for instance, but most of them agree that the best representation of the CSH structure is brought about by what is called the Feldman Sereda model. According to this, CSH is present in layers or sheets. Okay, you can see these sheets indicated on the diagram on the left. Okay, and some of these layers of CSH may be covalently bonded. Some of the layers may be bonded by weak van der Waals forces. That's more commonly accepted, that these layers are loosely held by van der Waals forces. Okay. There are molecules of water which are in between the layers, which we call as interlayer water. There are molecules of water which form a film on the surface, that is adsorbed water. There is bulk water in the capillary porosity, you see this is a capillary porosity marked as C, okay, and there are water molecules in micropores that can also happen, okay, and water between the small micropores between the CS layers. So again this is basically responding to this, and this corresponds to the interlayer water. So all this is represented quite nicely in the structure that you see on the left. Of course, to a person who is new to this subject, it may just seem like some guy randomly drawing lines and crosses and dots, but the idea is these crosses and dots are representing a structure that we seem to associate with CSH. Okay. Now again these sheets are randomly oriented, there is no precise orientation of these sheets, okay, which causes the cohesive nature of the CSH itself, and of course the extent of the capillary porosity is dependent once again on your initial composition, what is the water cement ratio for instance, like we discussed in the calculation that we made earlier, alright. So obviously from this structure the one aspect that comes out clearly is that CSH should have a very high surface area. Now there are different techniques of measuring surface area. One of the common techniques is adsorption technique. So you can do an adsorption on CSH surfaces either by water molecules or by nitrogen, and nitrogen absorption is quite highly favored, and that seems to suggest that CSH has a surface area of nearly 200,000 square meters per kilogram, okay, that is really fine. I mean the sheets are not fine sized, but because they are sheets there is a large surface available on the CSH. So you have 200,000 square meters per kilogram as the sorption suggested surface area of CSH. You know that using Blaine we associate the Portland cement to have a surface area of about 225 to 325 square meters per kilogram, more typically around 300 square meters per kilogram. So you see here CSH is a completely different entity as compared to your average cement particle, because of the cement particles being 3-dimensional granular objects, whereas CSH being a sheet, because of which it has an extremely high surface area. Now of course depends on the technique, you can actually show this surface area of CSH to be even as high as 600,000 square meters per kilogram, but we are not here to discuss the technique, but our idea is to try and understand what happens to the cement, which is a fine grained particle, how does it convert into a sheet like structure which has extremely high surface area. Now interestingly what people have found that if you heat cement during the early stages of hydration, if you do steam curing or heat curing, which we often do for what? For precast materials, for what? To increase the rate of strength development. We want to increase the rate of strength development, so we do heat curing or steam curing. Interestingly, it turns out that the surface area of the CSH that forms as a result of heat curing is about 7,000 square meters per kilogram. Now this suggests that you are leading to a different gel structure formation when you do steam curing. And indeed it turns out that steam cured concrete, while it gives you very high rates of strength development in the beginning, in the long term the strength that is attained by steam cured concretes is of a lower order as compared to the strengths attained by normally cured concrete. And that is happening primarily because you are creating more coarse porosity in the system. Why does it happen? You can imagine it in the early fresh cement paste system, when you increase the temperature you are rapidly causing dissolution from the surface of the particles, right. So in other words you are forming this hydrated barrier structure much faster, and you do not give a chance for complete hydration to take place inside, okay, in the early stages. So this coarse porosity in the outer CSH is greater in heat curing. Now what research has shown that the inner CSH seems to be even denser at higher temperatures. So the problem actually lies in the coarse porosity that is in the outer CSH, and that is of a higher extent in the case of your heat curing or steam curing. So this gel surface area that we are actually measuring is of the CSH that is in the outer CSH, right. The inner CSH we are not really bothering about in this case because we are not having a problem with heat curing in that case, right. Now what people have tried to do is associate the structure of CSH with some naturally occurring minerals. So here they have said that it resembles a combination of the structures of two different calcium silicates, one is called a genite, the other is called a tobomorite. Okay, but then the subject of structure of CSH is still under debate, but we do not have to really bother too much about it in terms of our understanding of concrete microstructure further, because I do not think we are looking at it from the perspective of cement chemists, we want to see it from the perspective of civil engineering. So again, this sheet structure obviously suggests that there is going to be very high either covalent or van der Waals forces, and the volume occupied in the paste is typically more than 50% of the paste. Okay, very large amount of the paste is occupied by CSH. Now, just to show this effect of the influence of temperatures, so these are cement mortars that were cast with different types of cements. So here you have an ordinary Portland cement, here you have a cement which is a fly ash based cement where 30% fly ash is present. Okay, so let us see what happens here. At 7 days, with an increase in curing temperature from 20 to 40 degrees, there is a minor increase in the strength, but when you increase it to 60 degrees, there is a decrease in the strength. By 28 days, you see that the strength is decreasing irrespective of the temperature. That means when you increase the temperature, the strength is dropping. Interestingly, in the fly ash system, it is not so. What is happening in this case, at 7 days, you see a fairly rapid rise between 40 and 60 degrees Celsius. Whereas by 28 days, you see that the strength drop that is associated with 60 degrees in the case of the OPC is not visible in the case of fly ash concrete. So generally, if you look at precast concrete construction, nobody wants to use fly ash because they feel that your rate of strength development will reduce when you use fly ash, and in fact in pre-stressed concrete, the use of fly ash is not even permitted in many regulations. But here you have evidence exactly to the opposite, that when you do heat curing with fly ash concrete, you actually obtain strengths which are not deteriorating in the long term. So there is positive advantage of using fly ash in precast pre-stressed systems, okay, especially when you are doing heat curing. When you are doing normal curing, of course there is no point, because definitely your strength gain will be reduced when you use fly ash, right, but heat curing definitely increases the rate of strength attainment with fly ash. Now what is also shown here on the right side is an example of how the porosity varies with different temperature, and this is determined with a technique called mercury intrusion porosimetry. So in this case, what we do is we have cement paste or mortar samples which are enclosed in a chamber, and we pressurize mercury into entering the pores. And you know very well again from the capillary equation that at higher pressures you will penetrate the smaller and smaller diameters of the pores. So all we do is simply penetrate or make the mercury penetrate into the pores under an increasing set of pressures. So the pore size distribution can as a result be obtained from this experiment. So you see here that as I am increasing my temperature, what is happening to my pore sizes? They are getting larger and larger. So I am coarsening my porosity because of increase in temperature. Okay, so that is the most important aspect about OPC concrete which is exposed to high temperatures, is that it will end up having more capillary porosity when you do heat curing in the system. Okay, so any system which you make to react in a fast manner in the beginning will ultimately attain a lower level of packing and microstructural development in the long term. So for example, if I use an accelerating chemical in the concrete and I get an extremely rapid rise of the first 2-3 days strength, in the long term I will see that my normally cured Portland cement without any accelerator will go beyond the strength attained by the accelerated system. Okay. Again, this is true of most things in life. When you try to attain something fast, the effects last only for a short period of time. It does not help you in the long term, right. So again, the old adage, there is no shortcut to success. That does not mean all of you keep striving for 30-40 years. There are accelerated paths to success also, but what you need to choose is the more sustainable path that will ensure that success stays with you for a longer period of time. Similarly, concrete, if it is slowly hydrated, if it is normally cured, it tends to develop a much better microstructure that leads to a long term strength and durability. What I've not shown here is the real effect on durability. That is even more drastic as opposed to the effect on strength. In the coarser porosity that is produced by high temperature curing, you actually get poorer durability of the concrete. So again, this race to increase the strength development in concrete may end up producing more detrimental effects in the long term. Okay. So again, another example of this influence of temperature. So this is a little bit of a confusion for you, because now I just told you in the previous slide that your strength is reducing as I increase the temperature in OPC. But what happens to the degree of hydration? My degree of hydration is going up as I increase the temperature. What do you think is happening in this case?
Pores are more, that's why strength is reducing.
Yeah, strength is lower because of higher porosity, but the high temperature ensures that the other processes that take place in terms of diffusion across the hydrated barrier, reaching the unhydrated particles, all that happens much faster than your normal temperature. So what you will see, what you will end up seeing is the inner CSH that is produced in the system, okay, will tend to have a much better density at higher temperatures. So what you will see is the calcium to silicon ratio of inner CSH goes up as the temperature increases. Okay, you see that this 1.99 to 2.18, there is a higher density of the calcium to silicon in the inner CSH at higher temperatures. What you will also see is there is a greater amount of sulfur and alumina inclusion in the system, and probably even alkali inclusion in the system. Okay, there is not, these results are not very conclusive, but definitely what people have shown is there is a greater extent of sulfur inclusion in the inner CSH at higher temperatures. So you are packing the inner CSH more densely at higher temperatures, which is leading to this increase in the degree of hydration of the clinker phases. Okay. Now there is also an issue of how to measure this, and some of this result may also be attributed to the way that the measurement is being done. So I am not going to go into that, we need to really think about that more clearly. Okay, so again, under elevated temperature conditions your CSH may be built differently, with a much denser association of individual nanocrystalline regions. In other words, what we are saying is we are making the CSH itself denser, but more outer porosity is created with the influence of temperature. Okay. Again, just some scanning electron micrograph images, this time of polished sections, which seems to show that as you are increasing in OPC from 20 to 40 to 60 degrees Celsius, just take a note at the outer grey area, not including the white cement particles, the outer grey area, what you can clearly see is there is a clear distinction in the extent of porosity at 20, 40 and 60 degrees Celsius. So there is a direct evidence, you can actually see this very clearly. A lot of literature is there existent in this subject, but what is interesting is when you do the same with fly ash, the result is not exactly as you see with Portland cement. There is a distinctly better performance when you increase the temperature with fly ash concrete.
But fly ash is not taking part in the reaction.
No, so when you increase the temperature, the reaction of pozzolanic reaction also increases. So fly ash is also increasing its reaction with the calcium hydroxide to produce additional CSH. So it is leading to more densification of your outer porosity. Okay, so what about the other products? We looked at CSH, what about calcium hydroxide? Calcium hydroxide is known to form as hexagonal crystals, and generally it is oriented tangentially to spaces available for it to grow. For example, pore spaces, areas around the aggregate and so on. Okay, you will find a majority of calcium hydroxide in pores and in areas around the aggregate. The very well developed crystal structure seems to indicate that the surface area is going to be low, 0.5 square meters per gram or 500 square meters per kilogram. So getting the same units, it is 500 square meters per kilogram. Van der Waals forces are low because very well formed crystals do not have any force of attraction between them. Gels or colloids will experience much greater forces that bind them, right. Volume is about 20% of the overall matured cement paste. Okay. So after CSH, this is the second largest contributor to the volume of the cement paste, and you can very clearly see the hexagonal crystals of calcium hydroxide that are forming in the system. Now what about Ettringite and monosulphate? There is a lot of debate about the structure of Ettringite, and we will revisit this when we actually discuss sulphate attack as to what type of Ettringite is actually produced and what type of Ettringite really causes expansion. But for the most part, Ettringite is seen as needles in the microstructure. It is basically columnar structure, but it is also hexagonal, which are seen primarily as needles in the system because you have very small dimension of the hexagon, and the presence of tubular channels between the columns can lead to a very high rate of water absorption. And the reason why Ettringite expands is primarily because it absorbs water, okay, and this absorption of water in a hardened concrete can lead to obviously expansion and cracking in the system. In the fresh cement paste, we do not worry about expansion because paste is still pliable, it can take the stresses created by expansion. Monosulphate on the other hand is a platelet, hexagonal platelet, okay, and the volume occupied by Ettringite and monosulphate is about 15 to 20%. So here you have Ettringite needles, very clearly you can see early age picture of the cement paste microstructure, you have a bunch of Ettringite needles that is forming, and you can see here monosulphate and Ettringite which are coexisting. You see some Ettringite needles also are there. The others look like needles, but they are actually the orthogonal view of the platelet. So it is actually the platelet, you are seeing the orthogonal view of that. So one more thing I told you earlier, that Ettringite and monosulphate are present in microcrystalline sizes, very small sizes. So you see here at least Ettringite is present in larger sizes, this 10 microns, the longer dimension of the needle can be easily 20-30 microns, whereas here this picture is taken a very high magnification. So 2 microns is this size, that means we are talking about not more than 4 to 5 microns of the area, I mean of the lateral dimension of the platelet. So these are not always easily distinguishable in your system. Even with techniques such as X-ray diffraction, you may not pick out sometimes the monosulphate because it occurs in very small crystals. So what we assume is monosulphate or other sulphoaluminate phases are present in a mixture with the CSH. Okay, the calcium aluminate hydrate, the monosulphate, these are assumed to be present as a mixture within the CSH. That is why we assume almost that this monosulphate is also an amorphous phase, whereas Ettringite will show up very clearly as a crystalline phase when you do techniques like X-ray diffraction because of this long needles that are actually forming in the Ettringite. The other important part of your cement paste microstructure are the pores and voids in the system. Okay, at the furthest end you have the entrapped air void. Of course, entrapped air void is not generally there in paste, it is more there in mortar and concrete because there is inefficient mixing that you do with the aggregates of the paste, and that leads to entrapment of air voids inside the system. We are talking about a few millimeters in size. Entrapped air voids are greater than 1 millimeter in size. Sometimes we want to wantedly put in air in the concrete to get good resistance against freezing and thawing. Okay, freezing and thawing produces damage to the concrete microstructure, so because of that we need better resistance. For that we actually provide spherical air bubbles in the concrete, and that is called air entrained concrete, right. Those are entrained air bubbles, and those are typically a few tens of microns all the way up to about 1 millimeter in size. Okay, and if you read the standards properly, it says that the air bubbles should not be separated by more than 200 microns. So it is not just the amount of air bubbles that is important, the spacing between the air bubbles also should be minimized to ensure that you get a good resistance to freezing and thawing. Okay, that is also one of the standards which we will revisit when we talk about chemical admixtures in concrete. Now in this region here where we are talking about 10 microns to 100 microns, you do not have anything, but you have something. What is that? Or probably even 5 microns to 100 microns. It seems to show that you do not have anything, but you actually have something. What is that? The unhydrated cement. At some size smaller than that, you have the calcium hydroxide crystals, hexagonal crystals, which is about less than 1 micron to about several microns. Okay, and you see those clusters of CSH, not individual CSH but clusters of CSH, that is of the size of, because you will not be able to see individual CSH because it is present at a nano level, right. So mostly you will be able to make out only clusters, which are several microns in size. Smaller than that you have capillary voids, which occupies a very large range, right, all the way from 10 nanometers to about 1 micrometer. Capillary voids are 10 nanometers to 1 micrometer, and then below the capillary voids you have the gel voids or gel spaces. In this case, interparticle spacing between the CSH, where we are looking at only about 5 nanometers in size, and maybe some small porosity may also be present in the less than 10 nanometer range. So, okay, so this is the extent of void spaces and particle sizes that you see in cement paste. Now, where is your sand grain? In concrete, if you extend this to concrete, where is the sand coming? This is the region for sand, maybe a little bit smaller, yeah, that is sand, and from here on it is coarse aggregate. Okay, so you see very clearly that we are ranging all the way from about 20 millimeters in the case of coarse aggregate to 1 nanometer in the case of the interparticle spacing between the CSH. So, we are dealing with a material that is having a wide range of particles and void shapes and sizes present in the system, because of which the properties can be quite complex. How these interact at different levels can lead to very different behaviors in concrete. Just one more indication of the types of porosity and also the technique for determining the porosity, that is also important. Depends on the limits of one technique, you will have to actually choose a different technique and so on and so forth. So, here you see that most of the techniques are either scanning electron microscopy or optical microscopy, but sometimes when we get down to gel porosity and CSH structure, we need to start using adsorption or mercury intrusion porosimetry or impedance spectroscopy. Okay, so, but for most of the larger features like ITZ, for example, microcracks, the scanning electron microscopy or optical microscopy is good enough to get you the features that you want to study. So, again this is indicating the sizes. So, capillary pores, as I said, are more than 10 nanometer, but again what we say is we have larger capillary pores between 10 microns and 50 nanometers, from which if you dry water it is not going to lead to large shrinkage, but from the smaller capillary pores 50 to 10 nanometer, when you remove water there is going to be very large amount of shrinkage. Gel pores, again you have small pores and micropores, these are very difficult to actually remove. Almost the micropores are leading to non-evaporable water, although earlier we said non-evaporable deals with the water that is bound within the crystalline structure, but here some micropores may be holding the water so tightly that you are not going to be removing that water at all. That we are talking about less than 2.5 nanometer size, and if you do mercury intrusion porosimetry you may not even be able to determine that porosity because of the extent of pressure that you can go to, right. Typically about 3 nanometers is the limit of what you get by mercury intrusion porosimetry. Interlayer spaces even less than 0.5 nanometer. So, you can imagine pulling out that water is going to be next to impossible. Your other features could include ITZ, which is about 20 to 50 micron in size, and microcracks, which obviously depends on the mechanism that has caused those cracks to appear in the first place. Okay. So, this is sort of showing you what people have done with different techniques to try and understand the nature of these pores and their distribution in the CSH or within the cement paste or concrete. Alright, there is a lot of further reading you can do obviously with cement chemistry. This subject I have only touched upon the tip of the iceberg, there is a lot more that is beneath the surface of the sea that you can't see, and there is a lot more studies you can do. Cement chemistry is still a subject of a lot of research around the world, primarily because people do realize that if you get down to the fundamentals of cement chemistry, you can actually explain a lot of the fundamental parameters and properties experienced by concrete and its service. So, primarily if you pay attention to cement chemistry, you can associate it with most of the other characteristics of concrete behavior that we will later learn about, like strength, elastic modulus, we will learn about aggregate paste relationships, we will learn about durability of concrete. So, you will see that all of that is related quite nicely to cement chemistry. Okay, so tomorrow we will start on the subject of aggregate in concrete. Thank you.